Okay, it looks like we've got a prism in the shape of an equilateral triangle made out of glass with a high index of refraction, n equals 1.5. Surrounded by air, so that'll be n equals 1. And we've got this ray of light coming in, originally going in along this straight up direction. And when light hits the surface like this, what would you expect to happen?
It goes straight through, no bending.
Yeah, in this case, it should just go straight through. In fact, in general, anytime light's approaching a surface perpendicular to the surface, it should just go straight through. Because if we draw out a normal line at that location, what angle does that ray of light make with the normal line itself?
0 degree angle. 0 degree angle.
Yeah, exactly. It's coming in at an angle of 0 degrees. And according to Snell's law, if the incoming angle is 0 degrees, the resulting angle should also be 0 degrees. Let me actually write out Snell's law here so we can refer back to it. We got index of refraction 1 times sine of angle 1 equals index of refraction 2 times sine of angle 2. So if theta 1 is 0, we get 0 for the entire left side of the equation, which means the right side also has to be 0. So if the incoming angle is 0, that is, if it comes in incident to the surface along the normal line, then it's going to have to leave along the normal line also. So anything coming in along the normal line goes straight through without any bending. And if we care about reflection, it would also bounce back without any redirection. So if it goes straight through, what's the next thing it's going to hit?
It hits the other edge.
Yeah, it's going to continue same direction and eventually hit this surface. So what we're going to need to do then is put in another normal line at that location. So if we draw in a normal line here, perpendicular to that surface, we can now say this is making some angle with the new normal line. So let's say we call this theta 1. And how would we find that angle? This angle here.
So the triangle at the very corner is the right triangle. So one of the angle is 60. So it's that angle that is next to the one that we are looking for. It's 180 minus 90 minus 60.
Yeah.
So we can.
Yeah, because we know this is a right angle. We have a 60-degree angle because this whole thing is an equilateral triangle. So what does this smaller angle up here have to be?
30.
Yeah, that's got to be 30 degrees. Because you can use the fact that the angles in a triangle have to add up to 180 degrees. And also as a shortcut for right triangles, if you've already used up 90 degrees of that, what's left for the other two angles?
Can you ask the question again?
If you've already used up 90 degrees, what's left for the other two angles?
90.
Yeah, another 90. It doesn't have to be a 60-30 split or a 45-45 split. It could be any split as long as those two acute angles add up to 90 degrees. But that is a useful shortcut. If you know it's a right triangle and you know one of the other angles, those two acute angles have to add up to 90 degrees. So that's just a shortcut to make it a little faster than setting the entire sum equal to 180 if it's a right triangle. And it looks like we have these two angles form a right angle. So what does theta 1 have to be?
60 degrees.
Yeah, it looks like theta 1 has to be 60 degrees here. So we've got that at least. Theta 1 is exactly 60 degrees. And at this point, I think we can apply Snell's law because we know theta 1 and we know N1 and N2, N glass and N air. In particular, before we even apply Snell's law, based on the fact that we're going from glass to air, slow to fast, what would you expect to happen to the angle?
It can be refract and reflect at the same time.
Sorry, what was that?
Refraction and reflection.
Yeah, we'd expect some to go through and some to bounce back. The bounce back, the reflection, has to be at the same angle. What should we expect about the angle of the refracted ray, though? Instead of maintaining the same angle with the normal line, what's going to happen to that angle if we're going from glass to air?
A bigger angle than 60 degrees.
Yeah, if we're going from slow to fast, slow light material, glass, to fast light material, air, that's an increase in speed, so we should expect an increase in angle as well. The ray of light is going to bend to make the angle larger, somewhat larger than 60 degrees. And we can find that angle by using Snell's law. So let's call this theta 2 for now. Again, the idea here is that the incoming angle splits, or the incoming ray of light possibly splits into a refracted ray, in this case with a bigger angle because we're going from slow to fast, and a reflected ray with the same 60-degree angle. Same angle in the sense that we haven't changed medium. We're going from glass to still in glass, so the angle doesn't change either. Any questions on that conceptually so far before we try calculating theta 2? So running Snell's law on this, we've got the first material is glass. So N glass times sine of theta 1, which is 60 degrees, has to equal N air times sine of theta 2, which we don't know yet. And we know N glass and N air, so we can fill in those values. N glass is 1.5, N air is 1. So how would we start solving for theta 2 here?
So 1.5 times sine 60 is 1.299, and then we take the cosine of that.
Yeah, 1.5 times sine 60, 1.299, you said? And if this were anything other than 1, we'd have to divide by that multiplier also, but the times 1 doesn't do anything, so we can ignore it. And before we take the arc sine of both sides, what do you notice about this that something's going to go wrong?
The sine value is larger than 1.
Right. Sine of any angle is always going to be less than or equal to 1. If you end up with if the algebra ends up as sine of something equals anything more than 1, that's impossible. This angle does not exist. There is no such angle whose sine is 1.299. There is no angle that works here. So that means theta 2 is impossible. There is no such angle. What does that mean conceptually? What does that tell you about the physical situation if theta 2 is impossible?
It's got all reflected.
Yeah, all the light gets reflected. There is no refracted beam at all. The refracted beam does not happen. There is no refracted beam at all. We only get a reflected beam, which, by the way, tells us that the reflected beam is the same brightness as the original incoming beam, because none of the energy leaves the prism. All the energy of the light bounces back. So we would call this total internal reflection, that none of the light leaves as refracted beam. All of it bounces back as a reflected beam. And specifically, a reflected beam at what angle?
60 degrees.
Yeah, that'll be another copy of 60 degrees. This is usually called the law of reflection, that the reflected angle, the angle of the reflected ray is the same as the angle of the incoming ray, the incident ray. So this is just another copy of 60 degrees. And if we extend that ray of light, because within the glass it's just going to travel in a straight line, It's then going to hit the other side of the other wall, the other side of the prism here. And to figure out what angle it hits this next side, we're going to need to use some more geometry. How could we figure out the angles involved in this this intersection?
So we draw the normal surface first.
Well, we're going to have to be careful about that. We got to figure out what, because it looks like this is maybe coming in maybe exactly along the normal line, or maybe just fairly close to the normal line. It's difficult to tell exactly just from the drawing. So how else could we figure out exactly what angle this ray of light makes with this side of the triangle?
So we can use that 90 angle again, and the top corner is the top angle is 60.
Yeah, this top angle of the equilateral triangle prism has to be what?
60 degrees.
Yeah, that's got to be 60 degrees. And I'm noticing we have just created a triangle here using these two portions of the prism side and this ray of light. Do we know any of the other angles in that triangle?
If we use the three angles 30, 60, and 60, and we take the sum of those three angles subtracted by 180 because it's a straight line, you would get 180 minus 150, which would be 30.
Yeah, so it looks like this has to be a 30-degree angle. Sounds good. And what does that tell us about the remaining angle of that triangle? Yeah, 30 degrees,
90 degrees.
60 degrees. Yeah, this has to be 90 degrees. So this is a right angle. And that means that this incoming ray of light really is coming in along the normal line. The ray of light is perpendicular to the surface. So that means it is coming in straight along the normal line. So what's going to happen to this ray of light?
Go straight through.
Sorry, what was that?
It goes straight through.
Yeah, it'll just go straight through. So this should be the path that light takes. The incoming ray of light hits the bottom surface of the prism and goes straight through because it's coming in along the normal line. It hits this diagonal surface and happens to bounce off completely because we get total internal reflection at that 60-degree angle. It then hits the next surface perpendicular to the surface, coming in straight along the normal line, so it's going to go straight through. And that's the only path light can take here. There's no other transitions it can make, no other divergences. Any other questions on that ray of light? Or any other questions about this this problem in general, or this behavior of light? And was there anything else we wanted to figure out here? I think that's about it, right? That's the that's all this particular practice quiz was asking. And by the way, another thing we could try out for the based on this total internal reflection thing, all we really did here was try out 60 degrees as θ1 and see if it works. And it turns out it doesn't. But there are some angles that will work and other angles that won't work. How could we figure out more generally what angles will work and what angles won't in terms of leading to total internal reflection? Like we found that θ1 of 60 degrees leads to total internal reflection. But we also know that if θ1 is 0 degrees, it will go through. So how do we figure out what's the boundary there between what goes through versus what reflects off?
The critical angle.
Yeah, there's a critical angle that's sort of the dividing line between what reflects off of it versus what gets through. Now, how would we find that critical angle?
So the critical angle we set as we can look at it as θ1, and then we set it equal to the n2 and sine 90.
And what do we want theta 2 to be? If we want to find the just barely case where the angle theta 1 is just barely big enough to make total internal reflection, yeah, we can set theta 2 equal to 90 degrees. Because the idea is if you've got a ray of light coming in towards the surface, specifically from the slow medium towards the fast medium, let's say you've got some ray of light coming in towards the surface, and we draw in a normal line. Closer to perpendicular. Yeah. So there's going to be some angle. I mean, for any angle that the incoming ray is coming in at, the resulting angle, the outgoing refracted ray, is going to presumably make a larger angle. If we make the incident ray make a larger angle, the refracted ray is going to be an even larger angle. And if we make the incoming ray a larger angle, the refracted ray becomes even larger. What's the largest the outgoing angle could be? Yeah, as soon as this refracted ray angle reaches 90 degrees, then it's not really leaving the surface at all. Like if we actually get that to 90 degrees, just skimming along the surface isn't really leaving. So as soon as the theta 2 reaches 90 degrees, there isn't really a refracted ray at all. So 90 degrees is our edge case here. So to figure out the edge case critical angle, that is the angle at which we get that sudden transition from it refracts to it doesn't refract, set theta 2 equal to 90 degrees. So that'll give us n1 times sine of, and I'm going to call this theta c for critical angle, equals n2 times sine of 90 degrees. So n1 times the sine of the critical angle, which we don't know yet, equals n2 times sine of 90 degrees. But what is sine of 90 degrees? Right, sine of 90 degrees is 1. So that just becomes n2 times 1, which is just n2. Divide by n1. And then take the inverse sine or arc sine of both sides. And we now have a formula for the critical angle. Inverse sine of n2 over n1, where n2 is specifically the faster material and n1 is the slower material. Because this only happens if you're going from a slow medium towards a fast medium. Any questions on the algebra there so far? And if we specifically try from glass to air, as in this example, let's try that out and see what we get. If we're specifically going from glass to air, theta critical is going to be inverse sine of n2, that is n of air, which is 1, over n1, n of glass, which is 1.5. So inverse sine of 1 over 3/2, that's 2/3. So inverse sine of 2/3. Anyone happen to have a calculator handy? What is the inverse sine of 2/3?
41.8.
41.8 degrees. Thank you. So that means if the incoming angle is 41.8 degrees or more, then you get total internal reflection. None of the light gets through. And whereas if the incoming angle is anything less than 41.8 degrees, that means it does get through. So that is, at least some of the light gets through as a refracted ray, and some of it probably bounces back in as a reflected ray also. But the important thing is some of it gets out. The only time you'd expect total internal reflection, none of it getting out, is if the incoming angle is 41.8 degrees or more, which is true for the theta 1 here. Theta 1 was 60 degrees, which is more than 41.8 degrees. So we get total internal reflection. Any questions on that so far? And by the way, note that we didn't actually need to know the critical angle to do this problem. We were able to just use 60 degrees in Snell's law try it out, find that it's impossible. There is no theta 2 that works. So we know that we get total internal reflection. But if you're going to be doing the same sort of refraction several times, like let's say you're going to have several situations where light from glass goes towards air. If you're going to have to do that several times, it's worthwhile to find the critical angle. And then you can just compare the incoming angle to the critical angle. Like if you see, oh, this incoming angle is 60 degrees, that's more than 41.8 degrees, the critical angle. So you immediately know it's going to totally internally reflect. Whereas if the incoming angle was less than 41.8 degrees, you'd know that some of it would leave. And that at that point, you would use Snell's law to figure out at what angle it leaves. But knowing the critical angle can often save time if you're going to be dealing with several interactions of the same two media, like glass and air, for instance. Any other questions on reflection or refraction so far? Or any other examples you'd like to try out?
I don't think we have any other questions, but I don't have any problem that I have on hand that I have questions about. But if you have anything that we can continue practicing on this
Let me
topic.
take a look. Let's see if I can find any other practice quizzes that would be worthwhile. So here we've got two lenses. We've got specifically a diverging lens and a converging lens, and it tells us the focal length of each one. We know how far apart they are. We've got an object that we don't know how far it is, but we do know the final image is 15 centimeters and upside down from lens 2. And what are we trying to find here?
The distance between lens 1 and the object.
Right, we want to find that initial distance from the object to that first lens. And we know that light from the object is going to hit lens 1. Presumably lens 1 is going to create an image. And also, moreover, since lens 1 is a diverging lens, what kind of image does it have to produce?
Virtual image?
Yeah, that's going to have to be a virtual image. So object 1 or lens 1 creates a virtual image of the object. And then what does lens 2 do with that?
Lens 2 flip it?
Yeah, lens 2 is going to create a real image of that object. Because we know that the image created by the first lens is effectively treated as the object for the second lens. Because if you take a look at the ray tracing here, I mean, without even really knowing the distances involved, if we just sketch out the rays, object 1 is going to create rays of light, which hit this diverging lens, and the diverging lens is going to make those rays of light spread out. So without even drawing in the principal rays, we can just get a rough sketch that the outgoing rays of light hit the lens and end up spreading out more than they were already, because this is a diverging lens. I guess it should be more like that. And of course, the ray of light towards the center just goes straight through. And of course, these rays of light don't intersect on the right side, but we should be able to backtrace to figure out where they seem to have come from. In fact, if we just ignore everything that happened before this, we can say these rays of light seem to have come from some point further back. There's going to be some point back here that all these rays of light seem to have come from. What do we call that point that all the rays of light seem to have come from? Yeah, that's the image. The image is this one point where all the rays of light seem to have come from. Since they didn't actually pass through that point, we call that a virtual image. But if we take a look at lens 2, as far as lens 2 is concerned, lens 2 doesn't really care about the object at all. Lens 2 is just thinking, well, these rays of light are coming in. As far as lens 2 is concerned, all those rays of light seem to have come from this one point, the image caused by lens 1. And since the point rays of light are coming from is the object, this point that rays of light seem to be coming from, even though it's really an image from lens 1, can be treated as the object for lens 2. Because as far as lens 2 is concerned, that is the point where these rays of light seem to be coming from. So conceptually, that's the reasoning behind this, that the image created by lens 1 is, for all practical purposes, the point where the rays of light seem to be coming from. So the next lens or mirror or whatever treats that point as if it was the object. Any questions on that so far?
Yeah, so really fast.
Mhm.
So how you would go about solving this is pretty much backtracking and starting with like lens 2 and going from the image, since we know the image, going back to find the object, and then use that object that you found as the image for lens 1.
Yeah, I think we are going to have to work backwards here, because in terms of the actual chronology of the direction light's traveling, light from the object goes through lens 1 and forms an image. Lens 2 treats that image as the object and creates another image. But we don't know the initial distance from object to lens 1, but we can work backwards from the final image, figure out where lens 2's object had to be. So let's start with that, working backwards from the end. Ignoring lens 1 and the actual object for now, if we just have lens 2 with known focal length creating an image 15 centimeters away, and by the way, should we treat that as positive 15 centimeters or negative 15 centimeters?
Because image is,
Yeah, positive should work here. Ultimately, because if you take a look at the direction light is traveling, light's traveling overall, especially at the end, light is traveling from left to right. And in general, we want to treat the direction light is traveling as the positive direction as far as image is concerned. So to the right is the positive direction. In this case, the image is on the right side, so we'll treat the image distance as positive 15. So considering just lens 2, we know image 2 is positive 15 centimeters. We know focal length 2 is positive 10 centimeters. The missing value would be object distance 2. And what equation will bring all those together?
The I over F equals or sorry, not the I over F, 1 over F.
Yeah, 1 over focus
Yeah.
is 1 over object plus 1 over image, the thin lens equation. We know the focal length, we know the image distance, and we're trying to find the object distance. So we get 1 over 15, and everything's in centimeters here, so I'm just going to leave off centimeters for now, equals 1 over O plus 1 over 10. And how would you isolate O here?
Aren't the numbers flipped actually? So it's
Oh, that's right. The focal length is 10. The image distance is 15. Thank you. Yeah, subtract 1 over I from both sides. So 1 over O equals 1/10 minus 1/15. Right, and then we'll take the inverse. We'll want to simplify this first. How would we simplify 1/10 minus 1/15? What's the common denominator we could use there?
30.
1/10 is the same as 3 over 30. 1/15 is the same as 2 over 30. So 3/30 minus 2/30 is 1/30. So O is 30 centimeters. In other words, the object, and I should call this object 2 is 30 centimeters behind the lens. So if we go back 30 centimeters away from lens 2, is where object 2 is. Presumably right side up because it gets flipped over to form a real image. So our image then, sorry, the object is going to be something like this. Don't know how big it is. Actually, I guess we do. If we got a 30 centimeters versus 15 centimeters, based on proportionality, what should be the size of this object compared to the size of the final image? How do these distances, 30 centimeters and 15 centimeters, compare to each other?
The height of the object should be double the size of the image.
Exactly. 30 centimeters is twice as much as 15 centimeters. That is, the object distance is twice as much as the image distance. So the object height should be twice as much as the image height. That's the whole principle of magnification. In this case, m would be -1/2 because the image is half as big as the object and flipped upside down. So that means lens 2 had to have had a right side up object that was 30 centimeters behind the lens. But of course, that object wasn't actually a physical object. That object was really what? Yeah, that object was the image from lens 1. So let's now take a look at lens 1. Lens 1, we should treat the object that we were using for lens 2 as actually the image from lens 1. So this we should call image number 1 versus object number 1. And for image number 1 here, what should we use as the distance between image number 1 and lens number 1?
Would it be 6?
Yeah, it should be 6 because it's 30 centimeters from lens 2, but that's only 6 centimeters from lens 1. And we can see that geometrically here, that if we've got 24 centimeters already used up out of the 30 centimeter distance, we've got 6 centimeters left here. We can also use the fact that the image distance 1 plus object distance 2 has to add up to the distance between lenses, which in this case is 24 centimeters. So if you fill in 30 centimeters for, actually for object 2, yeah, object 2 is 30 centimeters. So what does image 1 have to be?
It has to be -6, right?
Right. So image 1, if you subtract 30 from both sides, is -6 centimeters. So that's what we should use as the value of image 1. And that really just means if your image distance is negative, what does that signify? Yeah, exactly. It's a virtual image. Image 1 is a virtual image of the original object, which we can see partly because it's right side up, partly because it's on the same side of the lens as the object. Again, if you treat positive as the direction light is traveling from left to right and continues through the lens, continuing to travel left to right. So the right side, the direction light is traveling, should be treated as the positive side, but the image is on the other side, so we'll treat it as a negative value. So we know I1 is -6 centimeters. We're also told that the focal length is -10 centimeters, negative because it's a diverging lens. And it looks like object 1 is the unknown. We can at least use the D for that because that's the variable provided here anyway. And we can put all those together using the same thin lens equation. 1 over F equals 1 over O plus 1 over I. Focal length is -10, so -1/10 equals 1 over object distance is unknown, but we're calling that D. And then 1 over I would be -1/6. And then how would we isolate D here?
You add 1/6 to both sides.
Yeah, so 1 over D equals +1/6 plus -1/10. And common denominator there would be what?
$30.
Yeah. 1 over 6 is the same as 5 over 30. 1 over 10 is the same as 3 over 30. So 5 minus 3 would be 2 over 30 or 1/15. So D, if we just invert both sides, would then be 15 centimeters. So that's the object distance. This object had to have been 15 centimeters behind lens 1 in order to get this exact result. Any questions on that?
Yeah, actually, I've got another question.
Mhm.
So D, would it be, how do you know if D should be positive or negative? Like, how do you know?
Well, an object distance, if we're talking about an actual physical object, like an actual real thing that the light is coming from, object distance will always be positive.
Okay.
The only time you get a negative value for object distance is if you're dealing with a multiple lens setup. We know image 1 plus object 2 has to add up to the distance between lenses. If image 1 happens to be a positive number that's larger than the distance between lenses, you can get a negative value for object 2. And that's usually called a virtual object. It ends up behaving very strangely, and it's difficult to draw in the ray tracing, but the algebra still works fine. It is certainly possible for O2 to have a negative value. And that leads to some weird results, but the math still works out, and you can still calculate the location of the final image. But in all other circumstances, in particular, if you're dealing with an actual physical object emitting light towards the lens, an actual physical object will always have O being a positive value. You only get a negative O value as a possibility in a multiple lens setup if I1 is positive and larger than the distance between lenses. Any other questions on that so far?
Also, I had another question on divergent lenses. Is the focal length always going to be negative for them? Or how do you know? Okay, so they're just...
Ultimately, the reason for that is the thin lens equation, the 1 over F equals 1 over O plus 1 over I. You can derive that equation from scratch using a converging lens, drawing out the ray tracing, and setting up the geometry. It ends up being a result of comparing similar triangles in that diagram. So you could sort of think of the thin lens equation as specifically designed for a converging lens. But if you try the same thing for a diverging lens, it turns out that you have the exact same equation, but with an extra negative sign. But if you treat the diverging lens as having a negative focal length, then you can use the same equation for both. And that's really one of the main big ideas in physics in general, that if you can have several different scenarios, they can be all be analyzed using the same one generalized equation, a universal equation that covers many different situations. That's like the holy grail of physics, being able to create one equation that covers lots of different scenarios. And the thin lens equation is an excellent example of that. One equation that with no modifications needed can cover converging lenses, diverging lenses, converging mirrors, and diverging mirrors. You just got to be careful about what positive and negative signs you use for the values. But in general, this thin lens equation works for converging or diverging as long as you treat converging lenses as having a positive focal length and treat diverging lenses as having a negative focal length.
Okay, cool. Thank you.
Yeah. Any other questions on that? Or was there anything else we needed to figure out here? Looks like it's asking for the total magnification. How would we calculate magnification here?
We can use the equation where it's the height of the image over height of the object, or negative I over O.
Yeah, and
That's
the
one I
ratio of,
used.
yeah, the ratio of heights is the definition of magnification, like the ratio of image height versus object height is what magnification means. We don't really have any heights here, but we can use the fact that magnification also equals negative image distance over object distance. So if we try M1 and M2 separately, magnification 1 is negative image distance 1 over object distance 1. M2 is negative image distance 2 over object distance 2. So if we fill in those values, negative I1 is negative 6 centimeters. O1 was, it turned out, 15 centimeters. And then for lens 2, we got negative I2, which turned out to be 15 centimeters over 30 centimeters. Yeah, I think that checks out. We got -6 and +15. And on the lens 2, we got +15 and +30. Simplify that, we get negative cancels out. So 6/15 reduces to 2/5, or 0.4. And then magnification 2, 15/30 reduces to 1/2, so -1/2. In other words, lens 1 creates an image that's 2/5 the size of the original object. Note that this is not to scale at all. 2/5 the size of the original object and right side up because it's positive. Lens 2 creates a new image that's half the size of the previous object, that is half the size of that image from lens 1, and flipped upside down. And now that we know both magnification factors, how do we combine them to find the actual total magnification of this whole system? Yeah, a magnification factor is at heart a multiplier. So if you want to combine several magnification factors, you just multiply them together. So the total magnification, M1 times M2, 2/5 times -1/2. The 2's cancel out, we get -1/5. And what does that mean? If the total magnification is -1/5, what does that tell you about the final image?
That it's flips and smaller.
Yeah, flipped over because of the negative as compared to the orientation of the original object. And yeah, demagnified, smaller, specifically how much smaller?
5 times.
Yeah, or I would say 1/5 as big. The final image is 1/5 as large as the original object in terms of height and also width, any other dimensions, because it should be proportional, that it's 1/5 the size. Any other questions on that? All right, then I will see you next time.
Thank you.
You're welcome.